So, dear colleagues, today is our seminar, and we have a special guest who is a big friend of Ukraine and friend of mine from Italy, Professor Giancarlo Cravotto. He is a full professor of organic chemistry and vice director of the Department of Drug Science and Technology in University of Turin. He started his academic career after 1 year of experience in the Technische Universität Berlin and few years in the pharmaceutical industry. His research activity in the field of green chemistry, enabling technologies and process intensification is documented by more than 530 scientific papers, and he has index of Hirsch 74. He has also 20 international patents and several book chapters. He developed several non-conventional technologies applied from laboratory to semi-industrial scale, exploiting hybrid combinations. He is editor-in-chief of Processes and associate editor of editorial board, member of several journals by Springer, Nature, Elsevier, De Gruyter, Frontiers, and other companies. Most recent awards, it's a gold medal of I Paterno 2020 by the Italian Chemical Society, and the International Prize Emerging High Technologies in 2023, this year in Italy, as far as I understand, yes? Yeah, okay. So, dear Giancarlo, please, you can start your talk.
Yes, thanks so much, dear Valentin. I'm pleased to be here and to introduce this topic that is emerging enabling technology in chemical processing and highlight also really the true, which is the true in terms of real scalability of processes. Well, of course, we are all chemists. We love chemistry. I would like to introduce our group. It's a big group, also with several nationalities. And of course, it's always stimulating to work with young researchers. Well, today, speaking about emerging technologies in chemical processing, I would, at the beginning, to start with a bit more holistic view, and then moving to the strategies to reduce the gap between academia, research center, and industry. We are working since many years in process intensification. I'm an organic chemist, but often I'm doing the work of like an engineer. Of course, I collaborate strictly with several engineers because in the scaling up is fundamental. And then some perspective, so dream or reality, what is feasible and what is only a dream. Well, let's start as a professor in university, I think we all agree that it's really important, the storytelling in chemical education, because often we are considered like, enemy instead of ally, because the dirty chemistry, the pollution, and people often cannot see the positive aspect. Anyway, I don't want to spoil a good story now by telling the truth, but in the same time, honestly, we have to agree that lies spread faster online than the truth. So this is a fact. And you see, Science a few years ago published this editorial, and we all are often we feel more comfortable to hear lies instead of unpleasant truth that is quite common for humans. And meantime, perhaps you know the symbolism in Japan, in particular in Japan, but many other Asian countries in which this is a positive message from the three wise monkeys, that they will not see the evil, they will not hear, not speak. But in Western country, and in Italy in particular, is really not a positive message, but is a meaning of indifference, silence, or even complicity. Well, why I am showing you these images? Well, we may often find difficulties to recognize the true, even in high profile papers and journals. This because scientists in all the fields we will see are really now young scientists in particular in strong pressure for the career. And so we all have the high demand of gold publication, high number of citation, and this creates a stress and perhaps affect the quality of the investigations. I will not comment this slide. This slide, I think, is quite eloquent. We don't need to add other words. But well, we every day opening a journal, opening a magazine, opening a website, you are every day reading revolutionary result, revolutionary finding in different fields. So it seems that every day a new Einstein is reporting something new. Well, often critical aspect, drawbacks of the publication, negative aspect, perhaps on energy cost, scalability, or the environmental impact are omitted or are not fully reported. So this means that perhaps we are now in a period of poor ethical judgment. And we know, everybody know that there are many ways to make our results appear more attractive in a way that all has to be like really revolutionary or unbelievable new finding that and this is why we have in front of us a big window, that is the window of the social media, that in half a day we can spread our finding or what we are wanted to, to communicate, so the communication. And moreover, you can find universities, website, and many other opportunities that many people are more than willing to promote your science. Result is real well reported, so replication crisis. This is a main issue. This is a big problem, and now I am in the last part of my career, and of course I have many years in behind my story in the university, and I remember as a young researcher when I was searching in the library a chemical preparation for organic synthesis. Most cases I could really repeat and efficiently obtain the expected product. Now is more and more difficult, and I will not spend, of course, any words about patents, because for the reproduction of patent is even much worse. And this is not my opinion, but is what was published a few years ago in Nature, and you can see here a Nature survey dealing with the reproducibility and replicability in science. Really a critical situation. Many researchers were contacted and they released their own comment. And here you see the data. Unfortunately, as a chemist, we are in the top of the list. The question was, have you failed to reproduce an experiment? Of course, find in the literature, most scientists have experienced failure to reproduce results. And unfortunately, the number for the chemists is on the top of the list. Then, of course, it's similar for biologists, for physics and medicine and any other disciplines. So this is really the comment on the top was, let's not fool ourselves. So it's in some way, I would say, is a self-killing in terms of scientific value. One example is typically what I mentioned before, try to make the very most of the very tiniest. So the example of lithium-ion batteries. The lithium-ion batteries were introduced in the market in 1991, so more than 30 years ago. And every year we can find in the literature new publication telling, or publication or social media and web channel, university website, innovative or revolutionary lithium-ion battery. But well, in reality, what was changed in the last 30 years are only the electrolytes. And the real new innovative lithium-ion battery are expected only in 2050. So it's a future. So this is really quite eloquent and show that so research need time, and all what is presented as an innovative result is only a little finding at lab scale that cannot be industrialized. So we need innovation, in particular in chemical factor, that is not only to make money, of course. So chemical industry are deeply involved in manufacturing. So this is a nice book in the history of manufacturing, and the role of chemistry is fundamental. Well, we have to be efficient, effective, clearly. And this can be achieved combining a good balance of basic science and applied science. So I think in any lab, if you have a good balance among the two aspects of science, you could really have a new generation of chemists that have a much better view and opportunity for their own professional life. I often mention what was published almost 100 years ago, 1 century ago. So that is the great paradox of scientific research. And the usefulness of useless knowledge. This is the core or the soul of the research. That means new ideas are generated by basic science. So fundamental investigation. In our activities, we have different phases. So one is you have a process, in our case is a chemical process, and we are looking for an improvement, and we have an evolution. We are pragmatic, we can improve our process, but then you reach a plateau. The revolution is really completely different. It's disruptive, new idea, do it differently, and this is what really happened. You can improve your process, and then if you want to go further, you have to stop and you have to start with the revolutions, the reinvention. That it takes time, it needs money, it needs a big effort, but then finally you can reach a higher plateau, a higher level of productivity and quality. So this is more or less what is happened, and but generally speaking, the industry is open to new idea, but the problem is they are reluctant to abandon the old idea. This is the point. Nevertheless, 20 years ago, it was published in the Wall Street Journal. The pharmaceutical industry lags behind potato chips and laundry detergent makers in the use of modern manufacturing system. This was a shock because it's why. So you are thinking that the pharma industry is on the top on the technology, and then you realize that is really bad. 20 years later, this work was done 4 or 5 years ago in a commission by the FDA in the United States, and several companies, about 40 different companies were studied, contacted in several production sites, production plant, and the result was impressive. Pharmaceutical industry, this is referring to the United States, wastes $50 billion a year, $billion, due to inefficient manufacturing. This is, again, another shock 20 years later. What to do? How we can change this negative trend? Well, pharma industry is moving in the direction, the industry 4.0, where is looking from lab to real world, how to develop, how to scale up the big amount of data results achieved in lab scale, but only few of them can be really industrialized. And one of the main issues is the pilot level of investigation. So lab scale and industrial production are too far away. But who has to invest money in pilot scale? The research or the universities and research center are also reluctant to invest in pilot, and in more or less the same for the industry. So this is the connecting activity that is much more important, and now think slowly are changing. Well, lab, pilot scale, and full scale. This is a very nice Nature reviews in 2021. Well, scaling up reaction is easy to get wrong in a variety of ways. So it's much easier to make wrong instead of have a smooth increase of volume and productivity. So microgram to kilos remain an open challenge. Really is very challenging, and it requires also several expertise. It's not only a matter of chemistry, but several expertise have to join and work together. The trend in the last few years is in continuous flow, but even though you see fact or myths, the true is perhaps in the middle. We can have several reactions that take enormous advantage in terms of cost, in terms of impact, in terms of rapidity in continuous flow, in particular exothermic reactions, but in the same time, little production and reaction that occur relatively smoothly in batch have no reason to be developing continuous flow. So we have to evaluate case by case, but we cannot say the continuous flow or flow through chemistry is always better and cheaper than the batch. So it has to be clearly evaluated. Is a history that can be dated back or about 70 years. So the Italian company, international company, but well, located in Italy, Di Pharma, in the time it was Di Pharma Francis, the former dynamite. So they were producing nitroglycerins for, of course, medical application to treat angina and so several other cardiovascular diseases. That is, there are several preparations as acting on the, of course, on the blood vessel to have more perfusion of the blood. Well, in 1957, the engineer Mario Biazzi designed the world's first continuous production plant for nitroglycerin with remote control. So it was really, Antesian, so impressively focus on the future because the production of nitroglycerin is extremely exothermic, is dangerous, and in this way the productivity was regular, with high quality and with no risk. Well, what we can observe here is that in the last 13 years, we had not, in spite of the expectation, unfortunately, the number of examples of pharmaceutical preparation, synthesis, and downstream in flow mode is not as much as expected. Now we have plenty of reactor from any scale, little scale, big scale, but what we have to highlight, based on my experience, is that we need, based on your reaction, a dock-tailored reactor that can perform as you need. Anyway, we can highlight that the general trend is moving from batch to flow, also because the number of flow are relatively little, but we can see that from 2019 to 27, so in almost 10 years, 8 years, so the production, the manufacturing in flow is more than the double. So, but it takes time. Then you can improve safety, quality, you reduce space, and also you increase the product capability. Another important point as regards the pharmaceutical domain is that the FDA and the European EMA are passing quick approval for companies that transitioning from batch to production to continuous manufacturing. In the past, it was really complicated. The drug master file need a complete revision. Now is a bit more simpler. Well, even in flow, we can exploit a huge number of technologies that act in the direction of process intensification. Really a lot. Different way for heating, for example, the electric heating, microwaves or radio frequencies, or ohmic heating, exploiting the Joule effect, or infrared, or induction, or conductive. Well, only as regard heating technology, we have a list of possibility. We work a lot in the last 10, 20 years in the search of green enabling technologies for pharmaceutical synthesis and chemical conversion, with the idea that when feasible, when it makes sense, the flow can be better. And definitively the scaling up of microwaves, radio frequency, plasma, ohmic heating, ultrasound, hydrodynamic cavitation, or pulsed electric field take advantage by the flow, because the penetration depth of many of these technology, microwave, radio frequency, also ultrasonics, is limited. If you have a big batch, then you can penetrate only for a few centimeters. So for this reason, the flow is much, much better. As regards reaction in flow mode, we started in a very simple way, without any particular investment, modifying our HPLC pump. We were using a column filled with our catalyst, and then we tested a number of reactions, and we observed, in some cases, very, very good results by using this acidic silica, modifunctionalized silica, we could make interesting reaction in the epoxide nucleophilic opening and also in the cyclization of the quinoline Friedlander synthesis. So a good experience, and then progressively we try to make application or process for the industry. This is a patent with a company, and all this technology, microwave, ultrasound at different frequencies, were applied in the treatment of polluted waste from the industry. And this is an example for PCB dechlorination working in flow mode with this company that has plant in all Europe and also in South America. Well, again, we tested other reaction in a very artisanal way. We have a little company that makes some little tools. You see here this device to regulate the flow of the syringe. These were our reactor, were recovered column filled with our catalyst. Of course, then we move also to more evolved device, dedicated device for flow chemistry. It's an Asia series unit that was used to test our new catalyst for selective hydrogenation, so the selective hydrogenation of triple bond to double bond, avoiding the use of Lindlar catalyst. The Lindlar catalyst to make alkene from alkyne, and to avoid the presence of saturated derivatives, so really to stop at the double bond. It was quite complicated, but the Lindlar contained lead, and the industry don't want more to have lead in the catalyst. So we searched, we developed new catalysts, and results were extremely positive. Other tests were done moving from conventional to non-conventional technology, microwave, ultrasound, and this was our experience in the reduction of nitro group to aniline. But the curiosity was then what happened in flow. And so progressively we move using copper nanoparticles, try to work in flow mode. We filled our cartridges, and again, the results were excellent. Working in flow with this catalyst, the reaction was much faster, and the conversion as well. So although nobody has the magic stick, but anyway, it's the flow, reaction in flow offer really great opportunity. And then we repeated this reaction with several substrates with quite good results. Well, an extremely conservative journal, that is the Journal of Organic Chemistry, is now adapted to the time, and a couple of years ago, a new number was dedicated to enabling technology for organic synthesis. And in this way, the sonochemistry was presented. We explained the advantage of sonochemistry, a technology that is underexploited so far. So it offers big opportunity, even not only for the synthesis, but also for the crystallization. The sonocrystallization is a fantastic tool or technology to obtain crystals cleaner, same dimension, and avoiding also different crystal shapes. So it's a process that guarantees the quality of the crystals. The same with microwave. So microwaves also, the scaling up of microwave can only be in flow mode. No other possibility to produce in multi-kilo in batch. In fact, we apply microwave and other technology in the synthesis in continuous flow, working with the pharmaceutical industry and also with other companies in the search of more efficient technologies. This is one of the most recent example of application, very recent publication from batch to continuous flow of hydrogenation. It is the cleavage of the protecting group in meropenem. So this cleavage is in standard condition that is low. It takes several hours, and so we tested it in flow mode in microwaves. This with the flow synth, with the of course hydrogen pressure, and also working in our device that is a reactor, a flow reactor, in which we have the possibility to insert one, two, or several plates. And then we found that with 5 plates, we have a good compromise in terms of time and conversion. So this is the table that show that with 5 plates in at 50 degree, we could obtain an excellent results in the protection of meropenem. Well, sonochemistry, I mentioned already, is definitively a technology that has to work in flow. We have experience in batch, but in flow mode, you can do much more. The same is with hydrodynamic cavitation. This is a unit that exploits the hydrodynamic cavitation. In this case is in suction, so the pump is in suction, and then on the right also an ultrasonic probe, so combining hydrodynamic and ultrasonics. Then in the year we developed several cavitating tubes, actually like a cup horn, in which the cavitation occur around the tubes, and we inserted the tubing with a plastic with relatively good acoustic properties, mainly made in PEEK with a certain content of glass fibers to maintain. You know, some plastics are extremely bad for the conduction of the ultrasonic waves. And the same also with metals. This is a copper metal the tubings. In that time, the click reaction was one of the reactions more common in our labs, and we could generate in situ copper 1 by the disproportion of copper 0 in the reactor and continuously. Well, aiming to develop industrial process in continuous flow ultrasonics, we often start by using glass reactor in order to have a better visibility of what is going on. You see a unit that combines, so the sonication comes from the top and also from the bottom. So quite efficient. And then when all was working, it was typically, this was a reaction with two unmissable reagent, a reagent and a reactant. But then after some test, we find the condition to have a very efficient, very fast reaction, exothermic. We avoid to include in one reagent the non-reacted reagent that remain there. So after the visible reaction in Pyrex reactor, we move to reaction. Then of course you have to select the best metals. In this case, for the peculiar property of some reagent, we had to use hastelloid instead of titanium. And well, the results were giving us all the data for the real industrial setup that I cannot present for confidential agreement, but you can more or less imagine. These were tested also in reactor that we have, a flow mode reactor in our lab, and that can be scaled up with commercial available equipment that can guarantee already industrial productivity. These are some of our devices, also here, in which we can work in flow, in continuous flow. Example here already at industrial level, and here as well. Just a few words on the sonocrystallization. Sonocrystallization generate nucleus and then crystals grow, and we have equipment, we have everything to work at the industrial level. So the sonocrystallization is very common in some food industry and other also in alumina production. Well, in the pharma industry is starting now. In the last few years, some company decided to move to sonocrystallization, but still, honestly, we have to say that continuous flow crystallization under ultrasound is still underexploited. Advantages: you avoid the polymorphism, you have a very narrow Gaussian of the dimension, so many advantages. So just only to convince the industry that is the right solution. And some images. Well, the same is with microwaves. The industrialization is in continuous flow. Don't believe that the batch can solve any industrial problem. And in continuous flow, clearly you can manage with big quantity. This is work with the industry in which we had big scale production. Solochemical preparation, we prepare this alumina sphere loaded with palladium nanoparticles for the selective hydrogenation. This was very effective, and the reaction then was carried out in continuous flow in a microwave reactor. This is a general scheme of a flow mode reactor. Actually, you can buy the component, magnetron, waveguide, cavities, and then you can assemble. If you don't need a specific or a peculiar software, you can do it in a relatively easy way. You have a little cavity, or in the bottom you can see a longer cavity, much bigger, 80 centimeter long, and of course it depends which is the volume of your productivity. No problem then to move in a bigger scale. We have facilities, commercial available reactor for the industrial production. So at very high pressure, very high temperature, so microwave and radio frequencies, but in particular microwaves have an unbelievable accelerating effect on several reactions. These are a scheme of other application. Again, I have to highlight, based on your product, on your reaction, you have to design your microwave reactor ad hoc tailored for your application. Several common or at least commercially available devices are not suitable for these applications, and then you have to, unfortunately, to design a more appropriate device. These are examples, two different examples in which the feeding and the reactivity change on the base of the reaction. We did several experiments in flow mode. We prepared by ourselves the screw to make solid state reactions also. That is what we did. It's like an extruder, but in microwaves. We have several interesting examples of reaction, relatively fast and solvent-free. The same we can say about ball milling, so mechanochemistry. The evolution in terms of scalability in mechanochemistry is definitively the reactive extruder. So the reactive extruders, this is an example in our lab. are fast, are efficient, can be exploited, as you can see here, also for the synthesis of pharmaceutical product. Well, we are plenty of opportunity. We did also several experiments with the natural sources and so on. And still now work is in progress. We tested the reaction already carried out in ball mill, and we observed that in several cases, the reaction with a reactive extruder is faster and cleaner. Here you have the view of how we can start our reaction, and then very simple, very, very simple. This is in a vertical setup, but you can also work in horizontal setup. Nothing particular. Sometimes is needed a longer residence time in the extruder. So in this way, the conic screw twin screw extruder can offer an opportunity. We also exploited the recycling. You see that you have a little passage in which you can recycle your reagent, your reacting mixtures. In some cases, this is a very good solution, but it cannot be generalized. In a much more complicated chemical reaction, we combine, three different type of extruders to have a good mixing and to have also a good reaction outcome. So you see one extruder, then the second extruder for the feeding, and the third extruder that is a twin screw extruder, in a way that you can, in continuous mode, to perform a relatively complicated multi-step reaction. Well, this is again the setup of the extruder and several points of heating. So every extruder has at least 3 or 5 heating part of the screw, of the barrel, in which you can have different temperature for different point of the barrel. Some more detail for the twins in the twin screw, and then you see the extrusion, and and then what we can easily say is that scalability is feasible, just to increase the size of the screw. Well, I think I have more or less presented the main technology we use for the synthesis, and most of them also for the extraction. But I can present now some treatment of the effluent. We published several papers in the last 2-3 years for the treatment to clean, to make reusable the water or other type of waste in particular for pharma industry. Hydrodynamic cavitation is perhaps the most important and also historically exploited technology for water treatment, also in big scale. You see here a relatively big plant for water treatment, typically with the Fenton reaction. That would be with hydrogen peroxide and catalyst. Then we have also the use of ozone, so ozonation of the wastewater from the pharmaceutical industry, or also the chemical industry, or in some other cases, the liquid extraction. This is a prototype on the right here of a continuous flow liquid extraction. Very interesting also to improve then the quality of the extract of the wastewater. This is a setup, an industrial setup for the combination of ozonolysis, so ozonation, and ultrasound. This combination is extremely effective. It works very well, and we have got good results. For the fumes, we are mainly using plasma. Is very effective. Of course, it's not open in this way. This is only to show the four type of matter. So, of course, a solid, liquid, gas, and plasma, ionized molecule. Then we also have this type of unit for wastewater treatment, quite effective, in which the cold plasma may generate, in fact, plasma, and this is extremely efficient for the pyrolysis of several API that remain in the wastewater of the pharmaceutical industry. In conclusion, as a take-home message, I think the time is respected. I can say that if you think a technology can solve all your problems, probably you did not understand the problem as well as the technology. So no magic sticks, nothing, but only the selection of the technology based on your problem. So you cannot make general consideration for water treatment. These are the company that believe in the development of new technologies, and we have collaboration. And then if you have any questions, I'm really pleased to discuss with you and provide my opinion or answer. Well, thanks a lot for listening for this 1 hour of a seminar, and I thanks once more Valentin for the invitation, and you all for the kind attention. Thank you.
Thank you very much for your nice lecture. And dear colleagues, do you have questions to our lecturer, speaker, concerning first part of his presentation and the second part of the presentation?
Yes. I have a question.
Yeah, Victoria, please.
Yes.
Giancarlo,
yes.
Tell us how many liters or what volume of water can you purify by plasma technology during 1 hour?
Yeah, of course, the best way to treat the water, because normally our benchmark come from pharma industry, and I believe me, heavily polluted. Yes. So what we have to do is to dilute first. We have to dilute the water in order to have a much better performance. But the productivity is almost 1 cubic meter per hour. Mm-hmm. But then it depends on the type of pollutant. Clearly, there are pollutants that in one passage, it's over. You have oxidation, pyrolysis. Mm-hmm. In other case, you need the 3 passage or even 4 passages, because it depends on the chemical structure and the stability. The main phenomenon observed is just now we have some work on the waste of furosemide, that is a very common drug to increase the diuresis. It's we need more 2-3 passages. So but the process, the phenomenon is the pyrolysis. Strong oxidation and pyrolytic effect, because the bubbles, you need bubbles to generate plasma. And if you don't have salty water, you can work with the electrical discharge. Otherwise, you need a magnetron to generate plasma. It's if you have a high level of salt in the water, due to the ion that then can, of course, conduct the electricity. This is more, but in this setup, more or less, up to 1 cubic meter per hour. Normally, we are working with little volume because it's to avoid the stock, but this can be, and then you can have more than 1 column. So it depends. It's not particularly difficult. Thank you.
Oh, thank you. Thank you.
Thank you, Victoria.
Thank you very much. Other questions concerning?
Can I continue this question also
Okay.
with
Yeah.
purification? Hello again, Giancarlo.
Hello.
I'm wondering how plasma can purify from inorganic materials, because pyrolysis for organic, it's okay, and also organic materials can generate inorganic materials, chlorine or bromine.
Yeah, well, you have interaction, but the most magnificent result occur with the organic material, definitively. So, because with certain metals, it's better to we play with the chelants, with the resins. We can we are preparing also polymeric. Cyclodextrin that they can entrap, make a complex with heavy metals. So normally this process is much more efficient, or can be easily applied for organic pollutant. For inorganic, yeah, there are also other options.
Okay. I'm interested in this option because I was participated in the project for purification of drinking water by cold plasma. And I had this question and I could not receive the answer from my colleagues. But they say mostly that oxides can form some insoluble forms, and by passing through filters, they can be generally like removed.
Yeah,
is it true, or this is not for all metals?
Honestly, I'm not so much. What I know is only when the water contain too much salt, you cannot see the plasma with electrical discharge. So it doesn't work, or at least you have a very little. So you have to apply plasma. You have to detach everything. You have the magnetron. You have to use the magnetron. But in our setup, the electrical discharge is working better. We didn't focus our attention for inorganic because the pharma company has much more problem related to organic compound and API, so very active compound, in particular for antibiotics, that represent a huge problem in the environment for the antibiotic resistance. So we were really involved in project in which the main issue was destroy the antibiotics, mainly tetracycline and other metronidazole. We had several types of antibiotics that, thanks to the treatment, so the antibiotic activity disappeared. The molecule was not more detectable, and very little residue were found by MS, but for sure, several portions of the molecule were pyrolyzed to CO2 and water. Then, of course, the little compound remained.
So this is technology for killing organic impurities.
And very active for biological aspects. So all the microorganisms in one passage are completely inactivated.
For sterilization.
Yeah, absolutely.
My next question is about flow microwave reactors. As I noticed, you mostly in laboratory case use multi-mode reactors for flow reactors. Is this the same for industrial, or what is the problem with using monomode reactor, because you don't need to care about the volume of your reactor cell, and you can use more concentrated microwave power? Why don't you use it?
Yeah, the main issue is the energy consumption, that the efficiency in terms of energy, the monomode is less efficient. And at the industrial level, you have also, instead of 245 giga, you have also the 915 megahertz that have in which you increase the penetration depth. The new type of reactors offer the opportunity to monitor if the irradiation is not fully absorbed, the magnetron is stopped, you have a balance on the energy released and the energy absorbed. These avoid the leakage of microwaves or at least the overheating of certain part. This is a big advantage. But all the experience that I have at industrial application, just now we have a new plant that is under construction in Italy, big scale, and is in this case is, I would say, semi-continuous process with several reactors in parallel, and this is working at two multi-mode and 2.45 gigahertz. So this is our experience, at least.
So it's better to have more space in a reactor anyway, because it is safer for magnetron. And if it's necessary to do like very high temperature, you can use still monomode to just small reactor. Is it possible?
Yeah, normally is more small reactor, because all the company that built, and I know also company like so German company, UK company, also Italian company that produce industrial microwave reactor, and with a big, very high power. So it's several magnetron up to at least 10 or 15 kilowatt, means with several magnetron, but it's then you have a system to regulate, and
I
based on
understand
the flow,
interaction between magnetron irradiation.
the tuning, it works quite well. Of course, it's expensive. So if you see an industrial sonochemical reactor, also quite big, is much cheaper. What we did is to buy, we could also assemble by ourselves. So we bought by a German company the unit, and then we assemble it. We don't, in this case, we don't have a software, but at least you can manually regulate very well also the flow of the reactor and the power, everything. So, but at the industrial level, in particular, if you are working in pressure, then there are several issues for the safety. So you spend a lot of money for the engineering and for all the tests for the safety, in particular if you are working in pressure. So this is, it explains why I require a bigger capex, so that the capital investment is definitively higher.
And if it's possible, Valentin, my last question.
Okay, last.
Okay, this in your experience, if you need to separate final compounds by flash, and this flash is possible to do under atmosphere pressure only, how much scale you can reach for one reaction cycle?
You mean for the purification or for the reaction?
For the purification,
itself?
Isolation and purification. This flash column, like normal filter with silica,
yes,
and you can pass, but if you use pressure, the compound degrades.
Well, my experience, for instance, we work a lot with membranes. So if you are using only one cutoff of membrane, it happens that you can stop, but based on my experience, if you use a set of membrane and working ultra micro nanofiltration or up to the reverse of osmosis, so you can modulate your and you avoid the clogging. So in membrane, the volume are very, very big. If you are using column with, I don't know, silica or silica, then it becomes a bit more like chromatography is a bit more complicated. But with the resin, industrially, we use a lot of resins, ion exchange or other type of resins. The volume can be really big, and then works in continuous. I know company with polymeric, polystyrenic resins for purification, in particular for natural product. Then once every week, so one every 2 weeks, you have the wash in counter current, but they are well established at industrial level to purify and to works very well. If you are using the same product, it's simpler because then you don't have to clean every time the core, but really working in very big scale, several cubic meter also per hours. So with resins, but also membrane. So then it depends case by case, of course, type of purification that is needed. Is the purity are really a little portion or not? Difference of molecular weight, big tannin or little polyphenol easily separated, or to separate protein by sugars. So there are either affinity that are resins or molecular weight with membranes.
Thank you very much for
Okay,
your
you're welcome.
answers.
Thank you.
Here I have a question.
Please.
Yes.
Let me some words and some questions. Giancarlo, thank you very much for a very interesting lecture, but I have some question. I did not hear about lasers, about application of lasers in the synthesis, in technologies. Is it
Well, laser, my experience is only in lab scale to nucleate for generate bubbles for ultrasonics. So it's in the study of, so in nucleation, you can work with lasers. But based on I'm not an expert of lasers, but in bigger scale, the cost of energy is too high. And I know application, I show device for lab scale, but not at industrial, at least to promote chemical synthesis. Yes, in lab scale are quite convenient because you can generate a single bubble also in ultrasound is very interesting, or cavitation. To generate cavitation, laser can be applied. But then in big scale, there are many other applications, of course, of lasers. But in organic synthesis, at least I have no experience, and we never use it. No.
Thank you very much.
You're welcome.
Thank you. Dear colleagues, we have time for more questions if you have it. Yeah, Giancarlo, you started your presentation from the problem of reproducibility, and in the second part you will present mechanochemistry and extruders. What about reproducibility in this case? Because mechanochemistry is and reproducibility is a difficult story as far as I know.
Well, what I think is what is difficult in mechanochemistry is to find the best conditions, so the optimal conditions. But then when you really find the best working conditions, I think the reproducibility is not an issue. So it's we have several examples also at the industrial level with really good results. I can mention the oxidation of heterocyclic to desulfurization, the sulfurization of paraffin, in which with the solid catalyst, in particular the dibenzothiophene were oxidized to sulfone, and then the sulfone was washed with steam, water vapor, and this was absolutely reproducible and was working well. In the extruder is very similar. In the extruder you can have extremely reproducible reaction because you are working in flow, but the point is it's very easy to have a 50-60% of conversion, but then it's difficult in extruder to reach the 99% of yield or conversion. So, but when you reach the condition with to balance the share, which are the parameter, temperature, and in extruder is the share. So, which is the pressure that is needed, the mechanochemical power in the extruder. When you find the condition, then you just only feed and go. And so it is a continuous process. In ball milling, clearly it depends reactor to another reactor. You have to compare the same reactor, because if you change the conditions, so like a different company, different reactor, or different setup, different ratio balls and solid. Normally in ball mill, we are using 2 or even 3 type of balls to occupy the spaces. So big, medium, and little. So in 1/3 reagent, 2/3 balls, and then you can work quite efficiently. But in extruder, when you find the condition, the speed, the residence time, the temperature, the different temperature, then you can work in continuous flow for 1 year and just only feeding and collect. So it works very, very well. But now, just now, we are working for a reaction that is very important for the industrial application, but we cannot go over 77, 80%. Then we don't know why we have such a good conversion to 80%, and then the last 20 is still an open issue. Sometimes you have to create a condition for the cleavage of water, or to release the water, because it's a closed environment. So sometimes some product of the reaction remain inside, and so there are some aspects that require so investigation to reach the optima. So I would say the main issue in mechanochemistry and in reactive extruder is not the reproducibility, but is the reaction optimization that is difficult. If you want to only publish a paper, 80%, okay, it's fine, you can write a publication. But if you want produce to go in production, the industry normally say, we can discuss if you reach 90%, at least 90%. So if you are below, well, let's see, we cannot move in this direction. It's understandable, yeah.
Thank you. We have a question from Professor Vitaly Kalchenko, please.
Yes.
Hello. Thank you
Hello.
very much for your lecture, Giancarlo. Very impressive lecture. And my question is, do you teach this course, this specialty for students in Turin University?
Yes, actually it's a short course. I did much more technology. So I'm my department is drug science and technology. So we have pharmacists and pharmaceutical chemists and technologists. So these are the two. But then in terms of innovative technology, I teach longer course for food systems. Because the application of technology in food industry is much more relevant than in pharma or in chemical industry, because the food has some big volumes that compared to pharma, and then the regulatory affairs are a bit more open to, if you want to dry, I don't know, spaghetti or pasta with microwaves, if you want to dry with microwave a drug, a medicine, you need to have the approval. So the regulatory stop some improvement for pharma. But for answer to your question, I have one module for pharmaceutical chemist and technology, in which I'm teaching these technologies, only 20 hours per year. In food chemistry, and then I have another course in biotechnology. I have a course that is called enabling technology in drug synthesis and in drug discoveries and synthesis. That is for the course of biotechnologists. And in this case, I have 40 hours per year. Yes. There are courses. And
I
the courses
hope
are in English.
The course is attractive for students in Italy.
It's well, it's but then honestly, in my life, I saw I could appreciate more application in food industry, in innovative technology, than in pharma industry. You have a patent, you have data, you have everything, but then nothing changes. You still see the traditional way of production. If we are speaking about application of hydrodynamic cavitation or many other technology in food, cutting with ultrasound, sieving with ultrasound, heating, defrost, a lot of applications. Also for drying and for evaporation, so new technology for extraction as well, more than chemical synthesis. So in organic chemistry, organic synthesis, we saw some flow reactors, some application of non-conventional technology, but in terms of volume and application is still limited respect food industry, in which so just to tell the way in which Ferrero in our region is preparing the Nutella is not more the method used 50 years ago, of course. And many other examples are available of how the technology can improve the quality of the product and the stability, the safety, many, many aspects. Thank you.
Thank you.
Thank you. By the way, in my lecture for students of Kharkiv National University, it's modern method of synthesis of analysis, I use a lot of materials from Giancarlo's publications.
Thank you.
In the field of mechanochemistry, in the field of combination of different types of innovation technologies, and I present these results for our students in Kharkiv.
Thank you.
Yes, dear colleagues. Yeah, okay, and philosophic questions. Reproducibility, and in my opinion, the problem with reproducibility in publications connected not only with technologies, new methods, innovative methods, but also with just falsifications. And what do you think about possible ways to avoid falsifications and to increase reproducibility and quality of publications? Do you have some idea?
Well, we discussed among editor of journal many times, or it's difficult. But then there is another responsibility that come from the journal. The journals are looking to increase of course, the index of the journal, so of course, the impact factor of the journal, and the paper that, even if the content, but the paper in which the editor have the feeling that, oh, it will be a milestone, it will be really breakthrough, so they really will have a lot of citation, and then it's easy to publish because you are in a field in which, you know, the field of nano. For 10 years, nano had to be included in the now is different. In some way, the content is more, but the responsibility of the journal editor was in a way that consider paper that are that also the reader are expecting. Even if the content was not really scientifically relevant, but it is a bit more like a business, also for the journal itself. So or a big name that can have a bit more easy access to certain kind of journal because you have invitations. So perhaps you don't have such a relevant result, but you can replicate some your previous results. Is difficult, but the responsibility is of authors, editors, and so it is really to be divided to all the actors. So it's not easy. It's really not easy. And there are some editorial that were commenting this aspect. I think all the mentality of editor, authors, researchers has to change, but it will take time. I think it will not change rapidly. And then there is now ChatGPT or any other tool of artificial intelligence that can remodule the data and prepare the publication without any experimental investigation. This is crazy. This is really even worse. So the risk is that with the artificial intelligence will become even worse. So it's only fantasy and not really work in the lab.
Giancarlo, not only artificial intellect, now exists a market of small molecules, and you can buy these substances and tell us other way to these substances, which is not real way. This is very simple.
Yeah, but this situation with impact factors, with citation and so on was created exactly by scientific community, because it's a fighting between citations, between impact factors, and you can obtain any grants if you don't have high citation, if you publish your articles in low-cited journals and so on. But I think we should change the whole situation with this fighting of levels. So we should present quality of our research, but not quality of journal. It's in my
exactly. And in particular, multidisciplinary journal have a very high impact. In the field of organic chemistry, when I was a young researcher, it was nice to publish in, I don't know, synthetic communication or synthesis, singlet, tetrahedron letters. Now, they have a very low impact factor.
Yes.
And if you see other journals that are poor, so what means? I don't know. So is that the citation of an organic synthesis is like a niche interest. If you are speaking about, some salutistic aspect or some therapies or some material, the audience is much broader, and of course you grow in terms of interest. It's difficult, but also if you're working in a niche area, your work can be extremely valuable, of course, for a smaller group of people. But this area can be fundamental for the growth of the economy or any other scientific aspect. But I agree with you. So we have to think how to improve this trend that is a bit crazy. Yes. Many things now are crazy. So we are going in the crazy period in which the rationality seems disappears.
Yeah, I know. In Ukraine, we now have a very crazy situation because this crazy situation of world overlap with bureaucracy of Ukraine. And it's terrible. It's a real terrible. Okay, thank you very much. Our seminar, yes, I think we need to stop it. So thank you. Very interesting lecture and very positive discussion and very interesting discussion.
It was a big pleasure, Valentin and Victoria and all other colleagues. All the best, and let's be in touch. Hope to see in the next future very soon. Ciao.
Yes, ciao.
Bye, 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 bye.
Bye.
Have a good day.
Have a nice day.